Okay, well, I hope everybody's doing all right today. We're going to go ahead and continue with the notes we started yesterday. So if you misplaced it or you don't have some, I got them right over here by Adolfo in the filing system. Uh, so before we go ahead and get to that, just a couple things. We are at the end of the week, so next Wednesday by 8:05 in the morning, if you wanted to retake the test from earlier in this week, you can go ahead and do so. We still have quite a bit of time left on that. Going into next week, I'm hoping we should be able to wrap up this lesson, by Monday. We'll be able to take care of the word problems today, and then we'll get back to the packet on Monday. We'll get into the unit circle, but next Thursday we'll have our next quiz that's going to cover this material right here. And I am going to go ahead, because we're now about to start the unit circle, a few minutes at the beginning of every class starting next week. I'm going to go ahead and begin what's called MAD minutes. We're going to go ahead and start writing out the trig ratios, opposite, adjacent, hypotenuse. Well, MAD minutes because the time's going to get shorter as we go along. Well, I don't know. That's what they're called. I'm just going with it. Hopefully they'll make you happy. But once we get into the unit circle and we start looking at how to evaluate trig functions, also by creating the special right triangles, we'll start getting into that. And it's probably going to take us about a month and a half of us going through this. And I'm going to tell you guys ahead of time, it's probably going to get old. You hopefully will not get mad about it, but I guarantee by the end you're going to be really comfortable with the material, because in order to really do what we need to with the trig functions, we need to have a real solid foundation with those 6 functions and being able to evaluate them with triangles on the unit circle. So we're going to start that next week, and this is still a couple of weeks out, but I thought I'd go ahead and mention it as well. Your second exam is coming up on the 25th. So basically 2 weeks from yesterday. I'll have a little more information, as we get near the end of next week, when I hopefully have time to get those tests together. But I think that's it. I mentioned the quiz, the test, talked about our MAD minutes, or I guess I should call them happy minutes, because all math is happy. Yes, Lily Bell agrees with me. Okay. So does anybody have any questions? Hey. No? Okay, so let's go ahead and kind of review what we talked about yesterday. Now, this is, no, I need this. Okay, so we started talking about 2 concepts yesterday. Arc length, the distance around a portion of a circle, or basically a portion of the circumference. And we started talking about circular motion, which was made of linear velocity and angular velocity. So does anybody remember what was the formula for arc length? There you go. So S, which is your arc length, is equal to R, your radius, times theta. The only catch is that theta has to be in radians. Okay, so if it's given to you in degrees, there we go. It's not letting me write on it today. That says rad. Okay. So if it's given to you in degrees, we can easily go ahead and convert that. So the arc length equals the radius times theta. Now, then we went ahead and talked about linear and angular velocity, and we started getting into these real-world applications. Angular velocity is the rate at which the angle is increasing with respect to time. So basically, how fast is it rotating? Now, linear speed, linear velocity, on the other hand, is actually how fast an object is moving, just in a circular pattern. Basically, how fast are we moving around a circle? Okay, so we always started these problems with the same fraction. We needed to know the number of revolutions and how much time it's taking to do those revolutions. Seconds, hours, minutes, whatever it is we're talking about. But the thing about the angular velocity, we always like to measure it in what? In radians. Okay. So this second fraction is always going to pop up when you're looking at these problems. We want to multiply the number of revolutions over time by 2 pi radians in 1 revolution. Because what's going to drop out? Okay, the revolutions. Now we have radians per time. This is how you find angular velocity. You'll do the same thing every single time. So while this is angular, and we use that Greek letter omega, Looks like a curvy W, okay, to go ahead and represent that. There's one thing I can do to angular velocity, and I will immediately have linear. All you have to do is multiply by the radius. So if I take what I have here, multiply by the radius, it's now the linear. And what's going to happen when you multiply by the radius, that is a length. So it's going to be measured in something, millimeters, centimeters, inches, whatever it is. So as soon as you multiply by the radius and introduce that length, the radians are no longer necessary. Remember, we can associate radians with any length. Okay. And the variable for that was v. So we see omega, that curvy w, we'll say that's angular. That's the rate at which the angle is increasing with respect to time. If we see v, that's our linear speed. That is the actual speed an object is moving in a circle. Okay. So I think, help me remember. So did we get 2a done? We finished 1, but we did not get to 2. Okay, so I've already got 2 up here, so let's kind of walk through how 2a was created, and then we'll talk through b together. So the problem was we got a bike messenger riding his bike as shown with a 30-degree diameter, or 30-inch diameter. It says during one delivery, the tires rotate at a rate of 140 revolutions per minute. That's how you always want to start these problems. Even if they don't ask you for angular velocity, you always want to go ahead and find it because you can't find linear without having the angular first. So you'll notice I started by setting up my first fraction revolutions per minute. So the wheels are spinning at 140 revolutions per minute, so that's where this one came from. Now where did the second fraction come from? Remember, we like to measure our angular velocity in what? In radians. So this fraction, you're always going to see him pop up. It's always going to be the same. 2 pi radians in 1 revolution. And I got a text message here. Okay. So if I just stop right there, that's my angular velocity. So 140 times 2 pi, well, that gave me 280 pi, which is where the 879.6 radians per minute came from. Okay. Now, if I want linear velocity, I'm going to go ahead and multiply this guy by the radius. So let's take a look at what B says. On part of the trip to the next delivery, the tire turns at a constant rate of 2.5 revolutions per second. So you'll notice, dadgum, we can't use the angular velocity from part A because we've got a different number of revolutions per time, right? So it's like we're almost going to have to start over. So you always start the problem with the revolutions per time. So here, good God. Who's texting me? Okay. All right, so we have 2.5 revolutions in 1 second. So we always start these problems the same way, the revolutions per time. Okay. And then what's that one that always pops up? 2 pi radians in 1 revolution. So we can already tell when the revolutions drop out, I've got radians per second. So right there, if I were to stop, that is my angular velocity. Okay. But now this question here, B, is asking for the linear speed, the linear velocity. So how do I get that? What's the one difference? Just multiply by the radius. This is what introduces your length. Well, we have a diameter of 30 inches, so the radius is 15 inches. And for these types of problems, since we're going to have multiple fractions when dealing with the dimensional analysis, I always like to go ahead and put my radius over 1 just to make it a fraction as well, and it flows very nicely. Okay. So if I were to stop right here, I've introduced inches. The radians are no longer necessary because I have a length. It's in inches per second. That is going to be the linear speed. Okay, but it wants it specifically how? In miles per hour. So I'm going to have to change the inches, and I'm going to have to change the seconds. And it does not matter how you start. Do you want to start with time or the length? Okay, let's start with time. So let's just take it one fraction at a time. If I want the seconds to drop out, then for the next fraction, I got to put seconds up top. See, one above, one below, they're going to cancel. So we're going to change seconds to, whoop, got a little ahead of myself, to minutes. So what should my ratio be here? Yeah, there's 60 seconds and 1 minute. Okay. Now I want the minutes to drop out because we want hours. So I got to put minutes above, hours below. And again, it's the same thing. There's 60 minutes in 1 hour. So even though they're pretty far from each other, the seconds, one above, one below, they cancel. The minutes cancel. So right now, I'll have the speed in inches per hour. So see, we're getting closer to my goal. Is everybody okay with how I'm doing this? Okay. So now I got to go from inches to miles. So what's a good in between? Feet. Okay, so where do I have to put my inches? On the bottom, because right now the inches are on top, right? So I'm going to go ahead and put inches below, feet above. So in 1 foot, there are 12 inches. So now I've got feet per hour. One more and we're good. Where would the feet have to go? Okay, on the bottom, again, because I want those to cancel. So I'm going to put the number of miles above. Now, how many feet are in 1 mile? That is exactly right. 1 mile has 5,280 feet. So this is probably one of the longest ones we're going to be looking at. But see, just take it one step at a time. So let's go back. Let's see. My inches will cancel out. We made sure the feet would cancel out. So the only thing left is miles per hour. Okay. So now we just need to go ahead and multiply and divide all these values that I have. So let's see. I'm going to say 2.5 times 2 pi, and I'm just going to go straight across. Okay, so 2.5 times 2 pi times the radius 15 times 60 times 60. So this is going to give me the numerator, right? Now, what am I going to want to, what? What am I going to want to divide this by? There you go. I want to divide by the product of the two. So what I'm going to do here, I'm going to go ahead and say divided by parentheses 12 times 5280. I'm letting the calculator just take care of everything for me. So as soon as I push enter, I'll know exactly how fast the bike is going. So I'd say about 13.4 miles per hour.
Where'd the 12 come from?
Where did the 12 come from? The 12 came from when we were converting the inches to feet. And then we took the feet and converted that to miles. Okay. So here we go. We got about 13.4 miles per hour. Okay, is anyone not sure where any of those values came from? Yes, sir, Brandon.
I'm good in everything else except the red.
Uh-huh. Yes. Well, the revolutions cancel. We always want that to happen initially, right? But once you go ahead and multiply by a length, whatever that radius is, it's got to be measured in some way because it's an actual distance. So once you have that length, the radians just disappear. Okay. So we're not measuring the angle anymore, how fast it's increasing. We actually have a unit of measure to work with. All right. How are we doing? Okay, good. Well, all right. Let's take a look at this next one here. Okay, consider the DVD shown. So we have a DVD with a diameter of 120 millimeters. Find the angular speed of the DVD in radians per second if the disc rotates at a rate of 3.5 revolutions per second. So you guys walk me through this one. Okay, so Brandon says put 3.5 on top. So 3.5 revolutions, what? Over 1 second. Okay, you always multiply by that 2 pi radians over 1 revolution. 2 pi radians over 1 revolution. Now, every time you set up the problem like this, what immediately drops out? The revolutions. They're gone. So this is in radians per second, and that's exactly what we wanted, radians per second. So let's see, 3.5 times 2 pi would give me 7 pi. Will somebody help me out in the calculator? Isn't it like 21.99? Okay, so I would go ahead and, bless you. Ooh, there we go. I got it just in time. 22 radians per second. There we go. Remember, that is all that's required to find angular speed. You always start with the revolutions over time and multiply by this fraction. It will pop up in pretty much every single problem. Okay. Now in part B, if the DVD player overheats and the disc begins to rotate at a slower rate of 3 revolutions per second, find the disc's linear speed in meters per minute.
So put 3 revolutions over.
Okay, so Brandon says 3 revolutions over 1 second times, again, that same fraction. 2 pi rads over 1 revolution. Okay, so right there, that's my angular speed. But I am looking for the linear speed, so what should I probably multiply by now? Now, where'd you get 60? There you go. Okay, the diameter is 120, so the radius has to be 60. Very good. 60 millimeters. And again, just like before, I'm always going to put him as a fraction. Now, what is going to drop out now? The radians. Once you introduce that radius, the radians are gone. They always disappear. Now, the only thing is, my answer, if I stop now, is going to be in millimeters per second. We want meters per minute. Okay, so meters are going to be a little different. We'll see if anybody knows the conversion in just a second. Let's take care of the easier one. I want to change seconds to minutes. So where does the seconds have to go? Has to go on top. So minutes below. So 60 seconds and 1 minute. So when the seconds cancel, I've got millimeters per minute. So at the very least, I got that last part. Now, does anybody happen to know how many millimeters are in 1 meter? Oh, 1,000. That is right. Yes. That is absolutely right. 1,000 millimeters is 1 meter. So, if I want to get rid of the millimeters, where do I have to put them? On the bottom. Okay, so meters above. So 1 meter is 1,000 millimeters. Okay. So let's see if everything's going to work out. The millimeters are going to cancel. Okay. Looks like the only thing I have left is what they want, the meters per minute. Is everybody okay with what I've done? Is anybody confused? Okay.
When we take a test with this, if we have millimeters,
Yeah, if it's going to be something like that, I'll probably have the conversion up on the board. Yeah, if it's something like completely random, yeah. Mm-hmm. All right, well, let's go ahead and see. 3 times 2 pi, so I'm just going to multiply straight across the top. 3 times 2 pi times, what is it, 60 times 60? Okay. Now, that's the numerator, and all I have to do is divide this by 1,000. Okay. But, that's just going to move the decimal 3 over. So I would say we're looking at about 67.9 meters per minute. 67.9 meters per minute. Well, I thought that was kind of appropriate since, wasn't it Brandon a minute ago who was like, oh, baby. All right, how are we doing? Good? Okay. Well, let's take a look at this one. We got a wall clock, an old analog clock. It has a face diameter of 8.5 inches. The length of the hour hand is 2.4 inches. The length of the minute hand is 3.2, and the length of the second hand is 3.4. So we want to go ahead and determine both the angular speed and the linear speed for each of these 3 items. So we're going to go ahead and do one together, and then I'm going to go ahead and break you guys up to go ahead and try the other ones. Okay, now when we do this, the angular speed, let's go ahead and leave it in terms of pi. Okay, so we won't get the decimal on that one. Excuse me. And then for the linear speed, let's go ahead and say to the nearest tenth. So on the linear speed, we do want to go ahead and get that decimal. Okay, but not the angular speed. So I'll let you guys decide. What do you want to work together as a class? The hour, the minute, or the second? Okay, then let's do the second. Okay, so for our second hand here, we know that its length is, what, 3.4 inches? Okay, so 3.4 inches. So let's go ahead and find the angular velocity first. What was that variable that represented that? The curvy what? That curvy W, remember omega. Okay, so this guy right here. So how do we start every problem? The number of revolutions in time. So think about a clock. How long does it take the second hand to go all the way around? Okay, so one revolution in 60 seconds. Or could you even say, 1 minute? It's actually up to you how you want to start, okay, because they don't specifically provide that to me this time. Did you want me to go ahead and change that? Yes? Okay. Because it's the same thing whether I put, 60 seconds or 1 minute. Okay. Now what? Okay. Times 2 pi radians over 1 revolution. Okay. Now what? Okay. Revolutions are going to cancel.
Multiplied by the radius.
Okay. So it looks like we have 2 pi radians in 1 minute. And that makes sense. Remember, going the full circle in radians is 2 pi, and it only takes 1 minute to do a revolution. So there's my angular velocity. Got him done.
Wait, mister, I had to multiply by what's it called?
The length?
No, the short radius.
Oh, now here's the thing. This is a good question, and some people have been asking about this today. We always multiply by the radius, but in this question, it's kind of unique. We're talking about the tip of each of these items here. So the radius of the clock is 4.25. That's half of the 8.5, right?
I guess.
But am I going to go ahead and multiply the angular by that 4.25, or do I need something else? Don't take the difference. Remember, how long is the second hand? We know exactly how long, so we want to multiply by the length of that item. In that case, that would be considered the radius of its own little circle that it's creating, because all these have different lengths. Okay. So let's go ahead and take care of the linear velocity. Okay. Now, we can go ahead and start out the same way if you like, but we already have the angular velocity. So would you like me to go ahead and repeat the previous, or just go ahead and start with what we have? Okay. So 2 pi radians. Okay. In 1 minute. Okay. Now, it wanted the linear velocity in inches per hour. Okay. Well, the inches are going to be taken care of because that's how we're given the length of the second hand. So I'm going to go ahead and take the angular velocity, and I'm now going to multiply by the 3.4 inches over 1. So now it's inches per minute. But is there anything else I need to do? There you go. It wants inches per hour. So I got to get rid of the minutes. I'm going to put the minutes on top, hour below. Yes, as soon as we put in the inches, you're absolutely right. The radians are gone. And what's this ratio here? 60 minutes in 1 hour. Okay, so those minutes are going to cancel. And just like we've seen before, I'm left with inches per hour. Well, this one's actually pretty nice to us. I don't even have to divide by anything. I just need to go ahead and multiply all those together. 2 pi times 3.4, so let me get back over here. Okay, and it is not letting me do that, so I will go to my notes. Thought I was on a roll today. There we go. Okay, so what was it? 2 pi times 3.4? And then we had times 60, right? Okay. So I'd say we're looking at about 1,281.8 inches every hour. Okay, that's the distance that the tip of the second hand is traveling within that time period. And that makes sense because when you really think about it, it only takes a minute to do a full revolution. So it's doing 60 revolutions every hour. And each one of those is going to have a specific length. Okay. Any questions on that? Okay. Now, you're going to want to do the same thing for the other two. So let's go ahead let's see how many people we got here. How about I go ahead and do this? Everybody from Rozzy's row over, you guys go ahead and take care of the hour hand. Everybody else will go ahead and take care of the minute hand. So you're going to do the exact same thing. Yeah, so we're kind of stopping for just a second, sure. Can you do that? What does that mean? I've not seen that before. Is that what that means? Really? I've never done that. Really? Huh. So I guess when I see my son today, I'm like, hey, son, what's up? He's going to be like, you got to go to the bathroom? Let's see. All right, so I'm going to go ahead and give you guys 5 minutes. Okay. 5 minutes, and somebody from each group is going to come on up and show me what you guys found. So you definitely want to work together, help each other out.
I feel like we need more than 5 minutes.
But you're only finding, you're only basically solving one problem. So Lilybell's up to the challenge. Okay. I'll tell you what, I'll be generous. 6 minutes. 6 minutes, starting now. Okay, now on this quiz that I previously mentioned coming up on Thursday that's covering all this material, I'm going to go ahead and give you a larger bonus. It's going to be worth 10 points, so you could get up to 110 on this quiz. So a little bit of incentive, whoever comes up from each group will automatically get the bonus. Okay.
Is the bonus going to be like a math problem bonus?
Actually, no. I've already been talking to the other classes. I'm going to go ahead and do it on Venom. Do it on Venom this week. But again, Venom from the comic books. I haven't seen the movie. I don't know anything about that. So, yeah, go from the comic books. So you guys are doing the minute hand. No, B, I'll talk about that in a second. I'm going to make that a challenge problem. Well, we won't be doing it today. I'll show it to you on Monday. Jennifer? Uh-huh. So let's see. So you're doing the minute hand, 1 revolution in 60 minutes. Yes. So that's the angular. Okay. Okay. Oh, but it wanted it in radians per hour. So you just need to convert minutes to hours. Yes. But everything else is correct so far. Now remember, for the angular velocity, we're going to leave it in terms of pi, no decimal. For the linear velocity, we're going to go ahead and take the decimal to the nearest tenth, 1 decimal place.
Whenever that guy comes back with fast pass, can I go?
Sure. Right. Okay, so the hour people, talk to each other, help each other out. The minute people are talking. Hour people.
Sir, I don't get this.
You don't get this?
I don't get it at all.
Okay. Well, let's take it one step at a time. How do we always start these problems? What over what?
Hours over minutes.
The number of...
Inches?
No. What do we call it as it rotates around? What's the first thing to always drop out? The revolutions. So we always start with the number of revolutions with respect to time. So now you guys are talking about the hour, right? The hour hand. So let's take this hour hand right here. Okay. 1 revolution is going to take how long?
1 hour?
Well, 1 hour, see, he's only going to go from here to here. How long for him to go all the way around? No, not 24. 12. So 1 revolution is going to take him 12 hours. Okay. Now think about, like what we did with the second hand. We started off 1 revolution only takes 1 minute because he's traveling a lot faster than the hour hand is. Okay. What about the minute hand? How long does it take him to do 1 revolution? 60 minutes. There you go. Okay. Now, once you have the revolutions over time, what do you do? What's that one fraction that just keeps coming up? 2 pi radians over revolutions. Right there, that's your angular. Okay. Now, once you have the angular, how do you get the linear? You simply multiply by one thing.
The short line thingy, the radius.
The radius, that's exactly right. Yes. Yes, yes. Okay. Let's see if we can get that.
Wait, what are we doing? Are we doing the hour?
No, they're doing the hour, you're doing the minute.
Oh, y'all doing the minute. We keep the pi, right?
For angular, yes, we'll keep the pi. For linear, we'll take the decimal.
Yeah. Hey, Leo, so you put 3.2. Yeah, you put 3.2.
And I'll go to the screen right here. Okay. So we want to keep the angular velocity in radians per hour. And we want the linear velocity in, what was it? Inches per hour? Linear in inches per hour, yes. Okay. And it doesn't matter which one we do first. We can do the hour hand or we can do the minute hand. Okay. I've got 46 seconds left. And this is kind of how the mad minutes are going to work. I'm going to start calling them happy minutes because that just doesn't sound right. The happy minutes are going to work, but you'll be working by yourself given a time frame. Okay. All right.
Wait, so like that? Or would you divide that?
That's exactly right. Now just simplify. What is 2/12?
1/6.
That's it. That's your angular velocity. Very good. Okay, that right there is the 6 minutes. Who wants to come on up? Oh, Nathaniel's already on his way up. Okay, so you guys did the minute, right? Okay. So all I need is the angular and the linear velocity. Okay, so the minute hand makes 1 revolution. Oh, there we go.
And you multiply it by 2 radian
Over 1 revolution. Revolutions cancel. So now we have radians per minute.
And you get wait. I'm confused.
Now, you're absolutely right so far. We just wanted our answer in radians per hour. So all I have to do is change the minutes. You could if you wanted to, yeah. Yeah. So now it's going to be in radians per hour. Now, could he have also canceled out the minutes and still gotten the same thing? Absolutely, yeah. So 2 pi radians. That's exactly right. That's the angular velocity.
All right, then you multiply it by the length, so you have
Okay.
2 pi radian over 1 hour.
Okay. And in order to get the linear, we got to multiply by what?
3.2
Okay, the length of the minute hand.
over.
And we want our answer in inches per hour, so all we got to do is just multiply. This one will take the decimal. Okay. So what is 2 pi times 3.2? 20.1. That is exactly right. Oh, not radians. Remember, the radians dropped out. Inches. That is exactly right. Good job. Okay. Here we go. Drop them. All right, who wants to come on up for the hour? All right. And Nathaniel, if you'll go ahead and sign that for the bottom so I'll know who to give the points to. I do, please. All right, if you want to go ahead and erase that, we can. Yeah, just put it right below and I'll put fourth period on. Or fifth period. Okay, sorry. Okay, so we're going to start out. So one revolution takes 12 hours for that small hour hand to go all the way back around. Okay, good. Times the 2 pi radians in one revolution. Okay. All right. And we did want it in radians per hour. So all we have to do is just simplify. I'm sorry. So what would 2/12 become? 1/6, so pi over 6. Yes. That is exactly right. There's the angular velocity. Good. Now we're going to take that angular. We're going to multiply it by the radius, which will give me the linear. Thank you, sir. Okay, so this one we are going to approximate. So it looks like we need to take pi times 2.4 and then what? Divide by 6. Okay. Okay, that's exactly right. 1.25 what? Now radians per hour. Remember how long was the hand in what? Inches per hour. That's exactly right. There you go. Perfect. There you go, sir. If you will sign that for me. Good job. Good job. Okay, how we doing? Are we starting to feel a little better about the circular motion? Okay. Good. Okay. Thank you so much, sir. All right. So I'm showing 31. Okay, so why don't we go ahead and stop there today? If you'll go ahead and get your calculators back up on the front.